Welcome to today's Explainer. We're going to be looking at the true physics behind escape velocity. We'll break down exactly what it takes to leave Earth's grip forever, moving from the core math all the way to the actual engineering that has literally taken humanity to the stars.
Okay, let's dive into this. Just imagine throwing a baseball straight up into the sky. A gentle toss, it rises a few meters. A harder throw climbs higher before dropping back down. But imagine throwing that exact same ball so incredibly fast that gravity can never, ever pull it back. The ball just keeps traveling away from the Earth forever. Sounds crazy, right?
Well, for that to actually happen, the ball would need to leave your hand at exactly 11.2 kilometers per second. To put that into perspective, that is roughly 40,300 kilometers per hour. That's the magic number known as escape velocity from the surface of the Earth.
To get technical for a second, escape velocity is defined as the minimum speed an object must have to escape a planet's gravitational attraction without any additional propulsion. And it's that last part, without any additional propulsion, that is absolutely crucial because it kind of challenges everything we see in the movies.
Section 1. The Great Escape Myth. You see, most people picture space travel as a force problem, right? Like a rocket pointing straight up, engines blazing continuously, literally fighting gravity inch by inch. But in reality, it's an energy problem. Think of Earth's gravity as this giant, steep bowl. To get a marble out, you don't need a continuous, gentle push. What you need is one massive, energetic shove right at the start to give it enough kinetic energy to reach the rim and roll out completely. So the crucial point here is this: escape velocity is not about continuous acceleration. It's all about having enough energy. Once an object achieves this energy state, assuming we ignore air resistance for a moment, it no longer needs engines. It's already paid the energy toll to leave that bowl forever. Moving on to Section 2, orbiting versus escaping. So when we launch something into space, there are really only three possible outcomes. First, it goes too slow, and gravity just pulls it right back to Earth. Second, it goes fast enough to escape entirely. But the third situation? That's where the magic of orbiting happens. You see, the moon hasn't reached Earth's escape velocity. Instead, it's traveling sideways so incredibly fast that as it falls toward the Earth's surface actually curves away beneath it. It's continuously falling around the Earth. So orbiting and escaping, two completely different things.
Now, knowing that orbiting is basically just a state of continuous falling, here's a question for you. Does every rocket need to reach escape velocity? Think about all those rocket launches you see in the news, carrying astronauts and satellites into space.
The answer is a blunt and resounding no. Surprisingly, most satellites and rockets never even come close to reaching escape velocity because, well, they simply don't need to. They're specifically designed to stay gravitationally bound to our planet.
And comparing typical mission speeds brilliantly illustrates this. To stay in low Earth orbit, like the International Space Station does, you need a speed of about 7.8 kilometers per second. But there is a massive jump to the 11.2 kilometers per second required to actually escape Earth entirely. Only deep space missions ever need that staggering amount of extra energy.
Section 3. Real space engineering. Here's an engineering fact that might actually catch you off guard. Getting into orbit is actually harder than escaping. Sounds weird, right? But here's why. To stay in orbit, you can't just go up. You have to travel sideways at an extreme speed. When a rocket launches, sure, it first climbs through the thick atmosphere, but then it performs a maneuver where it gradually tips over. Eventually, almost all of its speed becomes horizontal. Simply pointing a rocket straight upward and firing would never produce a stable orbit. You just fall straight back down, kind of like that ball we threw earlier.
Now, what's really interesting here is how the math changes once you're actually up there. Escape velocity is not a fixed, constant number. The further you move away from Earth, the weaker gravity becomes. Up in low Earth orbit, you only need about 10.9 kilometers per second. Basically, you're already partway up the side of the gravitational bowl. Because the escape velocity drops as you get higher, engineers use this to their advantage to finally escape the bowl. Just look at the Apollo missions. They didn't shoot straight for the moon, no way. They entered Earth orbit first, and only then did the Saturn V rocket's third stage perform a massive translunar injection burn to give the spacecraft enough energy to leave. Spacecraft like Perseverance and Curiosity did the exact same thing for Mars. And those legendary Voyager missions? They gained enough kinetic energy to exceed not just Earth's escape velocity, but eventually the Sun's escape velocity, making them the first human-made objects to ever enter the uncharted wonder of interstellar space.
This historical strategy of entering orbit first is known as the parking orbit strategy.
If you're going to Mars, launching directly from the surface is just extremely risky and, frankly, inefficient. Instead, engineers put the spacecraft into a parking orbit around Earth. This brilliant three-step process allows them to, first, verify that all systems actually survive the brutal launch into space. Second, it lets them await in a stable holding pattern for the perfect planetary alignment. And third, they can perform a highly precise engine burn right from orbit, injecting the exact kinetic energy needed to overcome Earth's escape energy.
And this isn't just theoretical physics, by the way. This dictates every single aspect of spaceflight. Escape velocity helps engineers answer the most critical questions of a mission. How powerful does the launch vehicle need to be? How much heavy propellant must we carry? Which trajectory gives us the most efficient route? By calculating the exact additional velocity, or delta V as they call it, needed to climb out of that gravitational bowl, engineers can ensure the safety of the mission while keeping fuel costs as low as possible.
Let's move to Section 4, the big takeaways.
If you take only one thing away from this explainer today, let it be this fundamental distinction. Orbiting is simply the act of continually falling sideways around the Earth. You are still trapped in the bowl. Escaping is about possessing enough pure kinetic energy to break the bonds of gravity so you never, ever have to come back.
It's this very concept that has allowed humanity to leave our planetary cradle, walk on the moon, roam the surface of Mars, and even send probes out into the dark void between the stars. Which leaves us with one final, inspiring thought. Knowing what it takes to break the grip of gravity, if you had enough energy to completely escape Earth's gravitational pull, where in the universe would you choose to go? Thank you so much for joining me on this explainer today. Keep looking up and keep asking questions.